Hello, welcome to the course on Hadoop development offered by Data Raj Academy. My name is Venu and in today's session, we will have a quick overview of Hadoop architecture and Hadoop cluster. To get full advantage of this session, it is recommended to go through the session on computer cluster. You can find the link to that session in the description below of this video. I hope you will all find this session interesting and informative. In this session, we will focus on the very high level view of the Hadoop components. Hadoop is a complex system with many components. Some familiarity at a high level is helpful before attempting to build or install it for the first time. We will try to understand the various components of a Hadoop cluster in the real world. To get started, we will take Hadoop 1.X architecture to understand how the dynamics of distributed computing play together. One might wonder, when Hadoop 3.x is in the line, why are we still discussing Hadoop 1.x? For one simple reason, Hadoop 1.x architecture is relatively simpler and easy to understand. Starting with Hadoop 1.x will help us explore some of the fundamental features and strengths of Hadoop. This approach just makes our life easier to get started with and also gives us a complete picture of how Hadoop has evolved. In the process, we will understand the beauty of Hadoop framework and how amazingly it caters to the storage and processing needs of big data. Slowly in the following sessions, we will get to a point where we discover the limitations of Hadoop 1.x architecture, which eventually leads us to explore Hadoop 2.x and then Hadoop 3.x in detail. So let's get started. Handling huge volumes of data generated from various online activities and transactions requires continuous upgradation and evolution of big data technologies. One such big data technology is Hadoop. People often confuse Hadoop with big data. Let us be very clear about it. Big data is not Hadoop. There was big data before Hadoop and there continues to be big data without Hadoop. However, there is a reason why people tend to call it Big Data Hadoop. It reflects the popularity of the software Apache Hadoop in dealing with big data. But we have to keep in mind that there are other big data technologies apart from Hadoop, like NoSQL databases. Big data brings with it two fundamental challenges: how to store and work with huge volumes of data sizes, and more importantly, how to understand data and turn it into a competitive advantage. Hadoop fills a gap in the market by effectively storing and providing computational capabilities over substantial amounts of data. It is a distributed system made up of a distributed file system, and it offers a way to parallelize and execute programs on a cluster of machines. In this session, we will look at Hadoop from an architectural perspective. Hadoop is basically a software. It can also be referred to as a software library or a framework or a software platform. The Hadoop framework itself is mostly written in the Java programming language with some native code in C language and command line utilities written as shell scripts. Hadoop 0.1.0 was released in April 2006. The initial code that was factored out of Nutch consisted of about 5,000 lines of code for HDFS and about 6,000 lines of code for MapReduce. Hadoop continues to evolve to stand the test of time through the many contributions that are being made to the project, and hence it is still a popular and widely used big data technology. For example, initially only Java developers could utilize the Hadoop's MapReduce computational capabilities, as MapReduce programs had to be developed only in Java. This effectively hindered or limited the adoption of Hadoop technology by developers of other programming languages. This was a major concern. Hence, Hadoop streaming utility was implemented in the latter releases, using which any programming language can be used to implement the map and reduce parts of the user's program. This led to the wide adoption of Hadoop technology by developers of other languages like Python, C++, Perl, etc. Two important releases of Apache Hadoop are Hadoop 1.X and Hadoop 2.X. Hadoop is available from either the Apache Software Foundation or from companies that offer their own Hadoop distributions. Only products that are available directly from the Apache Software Foundation can be called Hadoop releases. Products from other companies like Cloudera and Hortonworks include the official Apache Hadoop release files along with some other ecosystem components that supplement the features of Hadoop and are integrated for specific purposes. But these products that are forked from and represent modified or extended versions of the Apache Hadoop source tree are not supported by the Apache Software Foundation. Hadoop versioning is often confusing because both Hadoop 1.x and 2.x are at times referenced using different version numbers. For example, Hadoop 1.0 is occasionally known as Hadoop 0.20.205, while Hadoop 2.x is sometimes referred to as Hadoop 0.23. By the end of 2011, the Apache Hadoop project was deemed to be production ready by the open source community, and the Hadoop 0.20.205 version number was officially changed to 1.0.0. Since then, legacy version numbering, that is below version 1.0, has been avoided, partially because work on Hadoop 2.x was started well before the version numbering jump to 1.0 was made, and the Hadoop 0.23 branch was already created. After Hadoop 2.x became production ready, we were seeing the old numbering less and less, but it still surfaces every now and then. Hadoop 1.x architecture is popularly called as classical architecture or MR1 architecture. Hadoop 1.x has two components. First component is Distributed Data Storage Framework, called as HDFS framework. This framework takes care of distributed storage of big data, and Hadoop Distributed File System HDFS is where the big data resides. Second component is the Distributed Data Processing Framework called MapReduce framework. Using this framework, we can process the data residing in HDFS. On top of data processing, MapReduce framework also takes care of the cluster resource management, that is, in allocating cluster resources like RAM, cores, disk space, etc. There were few serious limitations in Hadoop 1.x architecture. For example, huge amount of data residing in HDFS could be processed only using MapReduce framework. And MapReduce is a batch processing framework. This limited Hadoop's applicability only for batch processing jobs. Hadoop was not suitable for real-time data processing and interactive data processing. Hadoop is popular for its scalability, but after significantly scaling out for 4000 plus nodes, its performance starts to deteriorate. These and many other limitations threatened the applicability and usability of Hadoop as a big data solution. This resulted in the rewriting of Hadoop framework and the introduction of Yarn in Hadoop. Yarn is the foundation of the new generation of Hadoop and is enabling organizations everywhere to realize a modern data architecture. Hadoop 2.x architecture is popularly called as Yarn architecture or MR2 architecture. Hadoop 2.x has three components. First component is Distributed Data Storage Framework called as HDFS framework. This framework takes care of distributed storage of big data, and HDFS is where the big data resides. Second component is the Distributed Data Processing Framework called MapReduce framework. Using this framework, we can process the data residing in HDFS. But MapReduce framework is no more responsible for cluster resource management. The third and new component is Yarn, called yet another resource negotiator. Now, Yarn takes care of the cluster resource management, that is, in allocating and deallocating cluster resources like RAM, cores, disk space, etc. Hadoop 2.x resolves many of the limitations of the Hadoop 1.x architecture. Yarn allows multiple access engines, either open source or proprietary, to use Hadoop as the common standard for not only batch processing but also interactive and real-time engines that can simultaneously access the same dataset. That is, we can install Tez engine on top of Apache Hadoop for interactive data processing, or we can install Spark engine for real-time processing. Yarn's dynamic allocation of cluster resources improves cluster utilization over more static MapReduce rules used in early versions of Hadoop. In simple words, Yarn is much more efficient in cluster resource management. There are many merits that Yarn brings along with it. We will discuss about each of them in detail in the following sessions. Now, we will start by exploring the Hadoop 1.X architecture to understand the Hadoop infrastructure in detail. Hadoop 1.X architecture is relatively simpler and straightforward when compared to 2.x architecture. Hence, it will be a good starting point. Slowly, we will get to a point where we understand the limitations in this architecture. And this approach will give us a better view of the need for Yarn, which was incorporated in Hadoop 2.x. Apache Hadoop is an open source software that facilitates using a network of many computers, that is a computer cluster, to solve problems involving massive amounts of data and computation. It is a software framework for distributed storage and distributed processing of big data. At its core, Hadoop software is a framework that sits on top of a cluster of computers and allows for storing big data on large clusters of commodity hardware, and also allows to process that stored data. Doug Cutting, Hadoop's creator, likes to call Hadoop the operating system for big data. With its distributed storage and compute capabilities, Hadoop is fundamentally an enabling technology which enables a cluster of nodes to work with huge datasets. We will try to understand this with an example. Let us take our personal computer. Memory, hard disk, processor, and other physical parts of the computer come under hardware. We have to set up some kind of an operating system to utilize the hardware. An operating system is a system software which acts as an interface or intermediary between the hardware and its users, making it easier for the users to access and use other resources. On installing the operating system, all the hardware components of the computer becomes accessible. Like we can store the files in the file system of the hard disk. We can also install other utility software on top of the operating system, like some kind of media players or games, etc. The operating system is an integrated set of specialized programs used to manage overall resources and operations of the computer. These component programs of an operating system all exist in order to make the different parts of a computer work together. All user software, that is the application software, needs to go through the operating system in order to use any of the hardware, whether it be as simple as a mouse or a keyboard or as complex as an internet component. For a user who just wants to play a video file using a media player, it might look very simple because the moment we click on the file, it just starts playing. But there are a lot of series of events and programs and system calls that run in the background which are triggered by our single click. Operating system takes care of all these things in the background. In simple words, operating system is a specialized software that controls and monitors the execution of all other programs that reside in the computer, including application programs and other system software. The objectives of the operating system are to make the computer system convenient to use in an efficient manner by providing a simple and appealing user interface to the user, and the user does not have to worry about the details unless he or she wants to know specifically. To act as an intermediary between the hardware and its users, making it easier for the users to access and use other resources. To keep track of who is using which resource, granting resource requests, and mediating conflicting requests from different programs and users. To provide efficient and fair sharing of resources among users and other programs. To manage the resources of a computer system. Now, what do we mean by managing resources of a computer system? For example, memory management. Operating system keeps track of the primary memory. That is, what part of it is in use and by whom, what part is not in use, etc. and allocates the memory when a process or program requests it. Processor management. Operating system allocates the processors to a process and deallocates the processor when it is no longer required. File management. Operating system allocates and deallocates the resources and decides who gets the resources. It also does job accounting by keeping track of time and resources used by various jobs and users. Operating system takes control over system performance. It records delays between the request for a service and from the system. Often, users can interact with operating system in multiple ways. Popular way is through a graphical user interface. For example, in Windows-based operating system like Windows 10, we have clickable icons. Interaction may also take place via the console of the computer in the form of instructions like command prompt in Windows-based systems. The operating system acknowledges the same, performs the corresponding action, and informs the operation by a display screen. Error detecting methods and recovery mechanisms are also inbuilt into the operating system. Operating system maintains dumps, traces, error messages to handle failures. Operating systems that support multi-users also coordinate and assign compilers, interpreters, assemblers, and other software to the various users of the computer system. The list goes on. Now, imagine three computers, node A, B, and C, each with identical hardware configuration. These nodes are interconnected to form a cluster and can communicate with each other when in need. Each node has its own operating system, and let us assume it is Red Hat in our case. These operating systems cater to the needs of their respective systems on which they are installed. On installing Hadoop on this cluster of computers, it forms a common layer which is common to all the member nodes and coordinates them to work together with combined aggregated computational and storage power. Hadoop acts pretty much as an operating system but for a cluster of computers. That is, what an operating system like Windows 10 or Red Hat Linux does to a single computer, Hadoop does the same for a cluster of computers. Duck cutting, Hadoop's creator, likes to call Hadoop the OS for big data. With its distributed storage and compute capabilities, Hadoop is fundamentally an enabling technology which enables a cluster of nodes to work with huge datasets. As already discussed earlier, Hadoop 1.X is popularly called as classical architecture or MR1 architecture. Hadoop 1.X has two components. First component is distributed data storage framework called HDFS framework, where HDFS stands for Hadoop Distributed File System. And the second component is distributed data processing framework called MapReduce framework. Using this framework, we can process the data residing in HDFS. On top of data processing, MapReduce framework also takes care of the cluster resource management. That is, in allocating cluster resources like RAM, cores, disk space, etc. We have discussed the concepts of distributed storage and distributed computation in the earlier sessions. Now, let's see how Hadoop implements those ideas. We will now take a simple and small cluster of 4 nodes to understand the simplest possible Hadoop configuration. So, we have 4 nodes A, B, C, and D with identical hardware configurations. These nodes are interconnected to form a cluster and can communicate with each other when in need. Nodes are computers that are used as servers. A computer cluster is a set of connected computers that work together so that in many respects they can be viewed as a single system. Each node has its own operating system, and let us assume it is Red Hat in our case. These operating systems cater to the needs of their respective systems on which they are installed. Now, we have installed Hadoop on this cluster of nodes. On installing Hadoop, various software components or processes of Hadoop start running on the nodes. On node A, 2 Hadoop processes called name node and job tracker are running. On node B, 1 Hadoop process called secondary name node is running. On node C, 2 processes called data node and task tracker are running. And it's the same in the case of node D, where data node and task tracker processes are running. These Hadoop processes interact and communicate with each other at regular intervals and bind the nodes of the cluster together to form a unified system. That is, these Hadoop processes together act like an operating system that sits on the cluster and manages the combined cluster resources. Out of the list of Hadoop processes we just mentioned, name node, secondary name node, and data nodes are the processes related to Hadoop's distributed storage framework and assist in distributed data storage in Hadoop's HDFS. Whereas job tracker and task trackers are the processes related to Hadoop's distributed processing framework and assist in distributed processing of the data stored in HDFS. Hadoop processes running on the nodes of the cluster communicate with each other and coordinate with each other in managing the cluster. Hadoop processes are daemons running on the cluster. A daemon is a long-running computer program or a process or a service that runs as a background process rather than being under the direct control of an interactive user. For example, an operating system can be broadly considered as a daemon. It has to run continuously in the background for a user to access the computer. Daemon is a word in Unix environment. Equivalent of daemon in Windows is services, and in DOS it is TSR. Now, on a fully configured Hadoop cluster, running Hadoop means running a set of daemons or background processes on the different servers of a cluster. Hadoop daemons are long-running background processes that run on a cluster of nodes and respond to user requests. A point to be noted is that all the Hadoop daemons are Java processes and hence require Java runtime environment, that is JRE, to run. These Hadoop daemons have specific roles to perform on a Hadoop cluster. One should not confuse with the usage of the term node in the daemon name. Name node, data node, and secondary name node are the names of the Java processes running on physical nodes of a cluster. We will identify these hands-on in the following sessions when we install Hadoop. Hadoop adopted a master-slave architecture design for both distributed storage and for distributed processing. Now, what is a master-slave architecture? It is a model of communication where one process called the master process that is running on a node which can be called as a master node has control over one or more processes called slave processes which are running on slave nodes. That means on a fully configured Hadoop cluster, there are a set of machines or nodes which are master nodes, and there are other set of machines which are slave nodes. In case of Hadoop's distributed storage framework, name node is the master process which has control over all the slave processes, that is data nodes, in the cluster. That means amongst the set of HDFS related daemons, name node is the master process and data nodes are the slave processes. The nodes on which master processes are running are master nodes, and the nodes on which slave processes are running are slave nodes. Secondary name node is also a master process belonging to HDFS framework. Similarly, the master daemon or the master background process responsible for parallel processing of data is the job tracker. The node on which this job tracker process is running is called a master node. Task trackers are the slave processes which are controlled by the master process job tracker and are collectively responsible for parallel processing of data. The slave nodes in the Hadoop architecture are the machines in the Hadoop cluster which actually store data and perform complex computations. They can also be called as worker nodes. So to summarize, name node and data nodes are the processes that are responsible for distributed data storage in HDFS. Job tracker and task tracker processes are responsible for distributed data processing. Two slave daemons or background processes run on every slave node. They are task tracker and data nodes. Let us take an oversimplified example to give this understanding a proper shape. We will take a cluster with just a handful of nodes, say 5 nodes. Each node has its own operating system, and let us assume it is Red Hat in our case. These operating systems cater to the needs of their respective systems on which they are installed. Each node has its own memory and hard disk. We have also identified two types of nodes in the cluster: master nodes and slave nodes. Master nodes are the servers where the master processes are running, and slave nodes are the servers where the slave processes are running. Slave nodes are also popularly called as worker nodes for a reason. We will see why. It is basically on the slave nodes or worker nodes where the major action happens. On installing Hadoop, every slave node's hard disk space is divided for HDFS and non-HDFS purposes. Non-HDFS space is the allocated local space that is used by the slave node for its own local purposes, whereas the allocated HDFS space forms the part of the commonly shared and available HDFS. This is where the actual data is stored. That is, when there is a request from the client to store a file in HDFS, say sample.txt, the master process of HDFS framework, that is the name node process, takes the responsibility of making it happen. The request for storage from the client is first received by the name node. The name node process oversees the process of storing this file in HDFS. Depending on the size of the file, it is partitioned into blocks. That is, the file is broken down into smaller parts and stored in the HDFS. So, data is actually stored in the worker nodes by the data node processes of their respective nodes. We will look into every step of how HDFS read and write happens in detail in the following sessions. Similarly, all the computation on the stored data also happens in the slave nodes. When a client submits a job, the job tracker master process receives the request and oversees that the computation code is sent to each of the slave nodes where parts of the file are residing and computation happens locally. Once a client submits a job, the job tracker determines the execution plan by determining which files to process, assigns nodes to different tasks, and monitors all the tasks as they are running. The idea is to demonstrate that all the action, that is storage and computation, happens in the slave nodes and hence they are called worker nodes. Master processes only determine the plan and direct the slave nodes. That is, the master process job tracker directs the task trackers of the respective nodes and monitors them. We will look into every step of how a job runs in detail in the following sessions. We have also ignored the discussion on secondary name node for now, as it has no role in storage and computation. We will discuss about secondary name node also in detail in the following sessions. In the next session, we will discuss a little bit more about every process and their role within Hadoop. And finally, we want to hear from you. As the viewer of this tutorial, you are our most important critic and commentator. We value your opinion and want to know what we are doing right, what we could do better, and any other words of wisdom you are willing to pass our way. We welcome your comments. Your feedback will be enormously helpful in improvising the final shape of this course. So please subscribe to the DataRaj channel and contribute any questions, comments, or suggestions in the comment section below. Thank you.